All right, a sequence is a very special type of function. When students first encounter sequences, they often think of them as just a list of numbers in some particular order, and then they have to find the pattern. We will start with the technical definition of a sequence in terms of a function. So a sequence is a function whose set of inputs, or the domain, remember the x values, is a subset of the natural numbers. For example, 1, 2, 3, 4, and so on. A sequence is often shown as an ordered list of numbers called the terms or elements of the sequence. Sequence function notation can be tricky. So let's look at exercise 1. Consider the sequence below. If we represent this sequence with the letter A, then do the following. So we need to figure out what's happening each time. So 4, 8, 16, 32, 64, 128, 256. So, what could be happening? Could be 2 squared, 2 to the 3rd power, 2 to the 4th power, 2 to the 5th power, and so on. So it is 2 to the A power. Sorry, A power, not X power. 2 to the A power. So A is what you're going to plug in. So find A of 3. What this is saying is, what is the third element or the third one in line? Well, the third one in line is 16. Then we find A1 to plus A to the 7th. Well, 1 is 4 and 7, so 1, 2, 3, 4, 5, 6, 7 is 256, so it's 260. For letter C, find A of 2. That's just another way of looking at it. So A of 2 is just the second one in line, which is 8. Letter D says find A of 1 to the 2nd power. Well, A of 1 is 4 to the 2nd power is 16. Then we find A of 5 minus A of 4. So A of 5 is 64 minus 32, and you get 32. And then A of what equals 128? So we're looking at 128. It's saying at what number in the sequence makes 128? So 1, 2, 3, 4, 5, 6, and it has to equal 6. Sequences are functions. The key here is that the input is simply the numbers placed in line, so to speak, and the output is the actual number in the list. Consider the sequence defined by the formula A of n equals 2n plus 1. Write out the first 5 elements of this sequence. So 1, 2, 3, 4, 5. So the first one would be 2 times 1, which is 2, plus 1 equals 3. Then our second one, 2 times 2 is 4, plus 1 is 5. Our third one, 2 times 3 is 6, plus 1 is 7. Our fourth one, 2 times 4 is 8, plus 1 is 9. And our fifth number is 2 times 5, which is 10, plus 1 makes 11. So we're going to graph the sequence on the grid shown. So when x is 1, y is 3. When x is 2, or n is 2, y is 5, and so on. So you'll notice that I plotted all of the points, but I didn't connect the dots. The reason why you don't connect the points plotted when we're talking about sequences is because there are no non-integer inputs, meaning I'm not finding 1.5 sequence or 2.5 in the sequence. We're finding integer inputs, meaning we have to have integer outputs. So what is the 21st term of this sequence? The 21st term, how we're going to find that? We want to know what is the answer when n is 21. Well, you're going to do 2 times 21 plus 1. 2 times 21 is 42. 42 plus 1 is 43. Sequences can be defined by a classic function formula like what we saw in exercise number 2, so those are like linear functions. And they can also be defined recursively. A recursive formula is one where each term in the sequence depends on a term or terms that came before it. So consider a sequence of the numbers given. If the first one is 7, and then you end up with this weird little formula right here, where any number you put in for I is going to be I minus 1 plus 4. So to give a common sense interpretation of this recursive, we're going to look at our first term is going to be 7, because we know that b of 1 is 7. But it's going to depend on the inputs before it. So for our second term, it's going to be the second term minus the first term plus 4. So it's going to be the first term plus 4. The third term is going to be the third term minus the term in front of it plus 4. So it's going to be the second term plus 4, and so on. So you get each element by adding 4 to the previous element. So you add 4 to each previous element. So write out the rule for the first 4 terms and evaluate each one of them except b of 1, which is given. So just like we had over here on the left-hand side, so our first term is 7, right? So our second term is going to be b of 1 plus 4, which is going to be 7 plus 4, which is 11. Our third term is going to be b of 2, because notice how over here it's 3 minus 1 plus 4. Well, our second term was 11 plus 4 makes 15. And our fourth term is going to be b of 3 plus 4. So our previous was 15 plus 4 equals 19. So to write these in sequence, it's 7, 11, 15, 19. So when it asks you to write out the first 4 terms, you need to put them in a sequence like this. So one of the most famous of all recursively defined sequences is known as the Fibonacci sequence. So let's play around with it in the next exercise. The Fibonacci sequence is defined recursively as follows, where the first term is 1, the second term is 1, and a of n equals a of n minus 1 plus a of n minus 2. So how do you interpret this recursive rule? So this recursive rule, our first 2 elements are 1. So our first one is 1, and our second one is 1. But our third one is going to be 3 minus 1 plus a of 3 minus 2. And our fourth one is going to be, sorry, this should be an a of 4 minus 1 plus a of 4 minus 2. And then so to get to any term, you add the previous term. So to get to any term, you add the previous 2. So for a of 3, it's going to be a of 2 plus a of 1, which is 1 plus 1, which equals 2, right? Because 3 minus 1 is 2, which is where you get this 2, and 3 minus 2 is 1, which is 1. For a of 4, you're going to get a of 3 plus a of 2, which is going to be 2 plus 1, which equals 3. And for a of 5, you're going to get a of 4 plus a of 3. A of 4 is 3, a of 3 is 2, so it equals 5. So the sequence for 3, 4, 5 goes 2, 3, 5. Sequences often show up in the real world, where they're sometimes defined in terms of a recursive process. So Kirk is trying to train for the marathon. His first month, he runs 5 miles per workout. He adds an additional 3 miles to his workout for each month that he trains. So in month 1, he has 5. In month 2, we have to add 3, so it becomes 8. Then we add 3 more for the 3rd month, so he runs 11. Then we add 3 to the 4th month, so he runs 14. We add 3 for the 5th month, so he runs 17. So give a recursive definition for the sequence A of m. Don't forget to give an initial value. So our initial value is going to be 5. This is where it starts. So if we're going to write any recursive definitions, A of m is going to be A of the month minus 1 plus 3. So essentially what you're doing is all that A of m minus 1 is saying that the month in front of it, you add 3 to that value. So A of m equals A of m minus 1 plus 3, and your starting value is 5. And now all that we're going to do is we're going to graph these coordinate points up here. So when m is 1 at month 1, he was at 5 miles. At month 2, he was at 8 miles. At month 3, he was at 11 miles. At month 4, he was at 14 miles. And at month 5, he was at 17 miles. Just remember that you don't connect those dots because this is a sequence, a graph of a sequence, so it's not the same thing as a linear function.